Here's Delia with the other way, real quick, guys. What were we given at the very beginning of this problem? What kind of rational function? Improper. So what did I technically have to do before I even tackled any of that? What's all this? Make it proper. Well, long divide, do long division in order to get the whole portion and then the partial or the proper remainder. And that proper remainder I broke down into partial fractions. And so at the very end of the day, my answer wasn't just A, B, C with the proper denominators. My answer was the original x plus from up there and then the A, B, C to finish off the whole shabam. Does that make sense? Okay. But the first step was long division. Guess what the other way would also say? The first step, long division. That doesn't change, sadly. First step, long division. So I'm still going to say but after long division, we do get to where we have x plus 5x squared plus 20x plus 6 all over. The other way says, where do you go from here? Okay? The other way says, where do you go from here? You actually are still looking at, let me teach you. You're actually still looking at the remainder. And you're still breaking him down. You're still wanting it factored, which is how I wrote it. And you're still looking for A, B, and C. So technically, you're still going to get to what we would have said yesterday. Well, long division ended up being our step 1. Step 2 was factoring. Step 3, forming our partial. Step 4, multiplication. We actually still start off the exact same way. But when we get to here, there's another way of proceeding forward. Okay, so let me go ahead and put a star really quickly. You do all the same steps all the way up until right here. And you can come over to the other way. Instead of having to FOIL and multiply everything out, and then get out 3 different colors or use 3 different, like a circle and a square and a triangle, in order to think of grouping terms and making our different equations and then solving a system that's hopefully nice but could be nasty. That's hopefully nice but could be nasty. The other way says, basically, use special x values. Now technically, I don't just mean any special. I mean start with the zeros of the factors. When we go to a page that kind of has like everything all written out, like what we're doing and how we do it, it is going to mention the zeros. But in this example, we're going to see why when your classmates came up and was like, wait, I was trying to use the zeros and it didn't work. Well, you don't only have to use the zeros. But hold on. What are some zeros of this denominator, guys? What's 1 0 of this denominator, of these factors? -1. That's the 0 of this guy. And then who's the 0 of that guy? 0. So I'm going to say, okay, we're going to use 0, because he's kind of the easiest guy to plug in. Then we're going to use -1. Literally, we're going to actually write those x values, and we're going to plug in. Plug in where? Plug into the whole shabam. Let me show you what happens when we plug in. If we plug in 0 on the left side. If we plug in 0 on the left side, don't we just get 0 plus 0 plus 6? Well, that's not bad. I can play with numbers like that. If I plug in 0 over here, the a stays. 0 plus 1 is 1. 1 squared is 1. I'm just plugging in 0 and simplifying. Yeah? If I plug in 0 to bx times x plus 1, well, Joe's saying there's nothing there, but it's because he's already thought of, oh, 0 plugged in times anything, that'll just end up being 0. And then if I plug in 0 with c, well, 0 times anything is 0. So don't we end up with, really quickly, a equals 6? What? And we can trust that? Yeah, a equals 6. Doesn't it? A equals 6 over here. Well, that's a whole lot easier. All I have to do is keep track of some numbers. But that's only a. But what can I do right now in my equation up here? I can say I know a, right? Now, let's go plug in -1. Maybe it'll be nice too. Now, as soon as you go away from 0, it's going to be a little bit harder, but I mean, if you're in pre-cal, you can't be too terrified of numbers. And if you are, excellent, amazing job getting here, and I'm super proud of you. But we have to persevere through the fear of numbers a little bit. If we plug in -1 squared, that'd be a positive 1, yeah? Times 5 is 5. Why am I going to write -20 for my next one? 20 times a -1 plus 6 equals. So I have some more numbers to play with, but it's okay. I'm just plugging in -1. Now what happens if I plug in -1 right here? And 0 times anything is going to be? So maybe without even writing my 6 times, maybe I can just put a 0 to save time? What happens if I plug in a -1 here? Negative b times 0. Oh, nice. And what happens if I plug in here? C, -1 is negative c. So I can find c just by doing 5 minus 20 is -15 plus 6 is -9, or 11 minus 20 is -9. Wait, c doesn't equal -9. Nope, it doesn't. Negative c equals -9. So what does c equal? Does that agree with what we just found on the page before? I'm assuming yes, but I should probably make sure we're good. But yeah, c equals 9. Now here's the dilemma. We have and we have c, but what don't we have? But do we have any zeros? So we use 0. -1, can't really use them twice. Guess what? You get the exact same thing. So here's why I say use special x values to plug in. We use the zeros, and now we're done, and we need one more letter. So we're just going to plug in any random x we want. Let's plug in 52. Oh, I don't want to do the math with 52, do you? So special x, plug in something easy. We already did 0. We already did -1. Why not use +1? Does that make sense? So Joe, the answer to your question yesterday. Go use another random x value. Make it small and life will be easier. Did you have to use 1? Nope, you could have used 2 or 7 or 10 or any favorite number that you want to do all that math with. Let's use 1. So if I plug in 1, are we okay if I go 5 plus 20 plus 6? Plugging in 1 on the left side. Plugging in 1 on the right side. Okay, now we're going to have some math to do, but that's okay. There aren't going to be zeros. If I still plug in 1, 1 plus 1 is 2. 2 squared is 4. Are we okay with 6 times 4? We plugged in is 6. We're plugging in x is 1. Our b is who is still unknown, so that's okay. We're going to write him. He's still there. B plus 1 is 2. All you got to do, guys, is play with the numbers. Because over here I end up with a 31 equals 24 and 9 is 33. 33 plus 2b. If I subtract and get a -2 and then divide. Dun, 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 dun. Wait! Take them. Plug them in where they're supposed to go. Boom, boom, boom. Rewrite them with the beginning part of long division. And you're done. If you like numbers, the second way will probably be a lot easier. If you like seeing the entire thought process as to where it's coming from, well, okay, the first process is probably best. If you like numbers, the other way. And I'll call it the plugging in zeros way, but do you guys understand it doesn't have to just be zeros. That's why I said use at the very top. Use special x values to plug in. Start with the zeros because you have all these nice, yay, zeros, my life is better. But that's all right. If you run out of zeros, go plug in something else small and easy. Any questions? I know I have my quiet ones, my louder ones. What we could write for words, but I don't know if you need to. I don't know if you need to. The more detail on the other way is that we plug in zeros one at a time to our basic equation after we've factored, after we've formed our partials, after we've multiplied by the denominator. For repeated linear factors, like what we just saw, if you have something like x plus 1 squared, we have to make 2 different factors for it. One with this factor to the first and then to the second. Did anybody do homework? Did you see any cubes or fourth powers? What if this was a cubed? What would you have had to have kept doing? Yeah, but I said if it was a cubed, you would have done the x plus 1 to the 1, x plus 1 to the 2, and plus 1 to the 3. If it was to the fourth power and x plus 1 to the fourth, you make a separate partial fraction. This is like a little, what are weird things that can happen. You can use the zeros, and I say you can also use other x values too. If you have some sort of x plus or minus, because it could be with a negative to the n, you're just going to have to use this guy however many times in however many partial fractions. And then, Joe, here was the wording. You can substitute other convenient values of x if you run out of zeros, like you just saw us do. With quadratic factors, same thing. You expand it. They say don't really use zeros, although you could still use other convenient values. You can actually still use that. But with quadratics, what they're talking about is quadratics that can't be factored anymore, but we haven't seen any of those. They're saying just go ahead and multiply everything out and then, like term it, do the different color coding, and then use a system of equations. But I think we'll see one today where I'm going to say you can use this trick on that also. And then we just talked about that, plugging in zeros of factors. Doesn't have to just be zeros. Can be other x values too. So guys, you don't really need to memorize anything on this page. It's up to you. It's going to be up here for like a whole, I don't know, 10 more seconds if you want a picture of it. But otherwise, I think we're okay without it, and I think it'd be better to do some more examples. Cool? 5 more seconds if anyone wants it. So, what should we do? Let me prop open the door because it's kind of stuffy in here this morning. But after I do that, I'm curious what you guys would say is my first step. Ready, set? What's my first step? Joe? Long division? Why would someone think long division, though? It looks top-heavy. Doesn't it look top-heavy? He has 3 terms. He has 2 terms. But we have to remember, wait, top-heavy, you only care about the degree. Yeah. So since the top degree is lower, we're good. Whew, good, because that was going to be a long problem otherwise. Okay, now what? Matthew, what were you saying? Form the partial fractions? Yeah, but can anyone tell me what I need to think about to form my partial fractions? Matthew's saving his own answer. He said factor, right? So what happens if I factor that denominator, guys? Okay, so then keep factoring, right? Can I factor x squared plus 4? Find me the zeros of x squared plus 4. Remember, zeros come from factors. Factors come from zeros. We can work both ways. Okay, easy. We'll find the factors by finding the zeros. So x squared plus 4 equals 0. Some of you would have done this so illegally, because you would have said x plus 2, x minus 2, or x plus 2, x plus 2. But does this have any real zeros? Nope. So can I factor this more and keep it real? Not without going to 2i and negative 2i, and that's not real. So this is what we call an irreducible quadratic, if you see this anywhere. An irreducible quadratic means, guess what? You can't go down anymore. You can't break it down anymore. So therefore, when I go to form my partials, and I think you would have seen this in the first section of matching, one of these has an x and one of these has an x squared, and we can't break him down anymore. Yeah, because you can't factor it anymore. So this is what we call a quadratic factor. Now above anything linear, we just put an a or a b or a c or a d, because we need to make it 1 degree less. But guys, what's 1 degree less than a quadratic? 1 degree less than an x to the 1 is an x to the 0, but 1 degree less of an x squared is an x. Oh, crud. But I can also have, okay, that's why we have this weird bx plus c thing. or cx plus d or ax plus b, because we need it to be 1 degree less. We need it to be proper. We can't go straight to just a constant because there's allowed to be an x term and it's still proper. Okay, so that's something that maybe we didn't get to talk about before. What if you get a quadratic, he can't be factored down anymore? Okay, you keep him, but the top changes just a little bit. But the next step is the exact same, because the next step says, what do we do to both sides? Multiply to get rid of all the denominators. And to get rid of all the denominators, we use the LCD. Algebra 2 is playing with LCDs right now. The common denominators. The nice thing is, over here, it's super easy. The whole thing goes away. You're left with 3x squared plus 4x plus 4. But on this other side, when you go to put it in, if I were to put big parentheses, it would need to go across the addition to both. So it might be easier for some of you just to write it twice. Once, and maybe something gets lost along the way. So for this one, the second one reduces, but for this one, the first one reduces. And we end up with a times x squared plus 4 plus bx plus c times x. Now the book would tell you right now with this quadratic guy, the other way stinks. Don't use him. You better start foiling everything out and then color coding, get your x squareds, get your x's, get your numbers, make a big old system of equations. But I just said we can use the zeros. Just we're going to have to use some other convenient ones too. So if you guys, when we were solving just a second ago, if you were like, no, I get this way, then go, use this way right now on this problem. Multiply everything out, get all your x squareds, get all your x's, get all your constants, and then make a system and solve. But if you're like, but I like that way, do it with me because I'm going to do it that way. What would be a 0 that I should use? 0. Wait a minute, but that's my only 0. How many unknowns do we have? 3. 2 partials, right? But 3 unknowns. So guess what? 0 is going to be nice and all, but we're going to have to choose 2 more convenient values. It's up to you. Would you guys rather keep it positive and not have to worry about negative numbers and go like x equals 1, x equals 2, keeping it small to be easy? I guess you can go with 5s if you want, if you like 5s more. Or do you want to go smaller numbers? I don't care if it's negative, negative 1, positive 1. I don't care. You want 1, 2, or negative 1, 1? Negative 1, 1? Cool. I'm going to give you a little bit of a head start. Why don't you go plug it in? See what happens. With those 3 plugins, you should be able to get A and B and C, or at least have enough information to get them. If there's at least one 0, I say use it because life is nice plugging in that 0. Go as far as you can. I'll start playing, but sometimes I do it a little too fast and I lose some of you guys. And some of you love numbers. Careful, Joe. You don't want me taking off points for not enough examples. But good job getting a start on homework. Maybe get 0 plus 0 plus 4 equals A times 4. Did you guys realize this whole second piece becomes 0? B times 0 would be 0, plus C would be C times 0. Oh, it didn't even matter. It's just 0. So, you guys got it, yeah? A equals 1? Ha! We got one. Okay. This won't be bad. Psh. Silly book telling us it doesn't really help. Now don't worry, I would have still done it this way. I'm not leading you down like a horrible path to be like, ha ha ha, you didn't see what was coming. No, 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 not this time. I've done that before, I know. It's a life lesson though. But now we have to plug in, okay, you guys chose -1, that's okay. But -1, that'd be a positive 3, minus a 4, 4 times -1 plus 4. I can plug in a 1 for A. -1 squared is still a positive 1. 1 plus 4 is going to be 5. -1 times B is -B plus C times a -1. Okay, this is kind of messy, but hold on, hold on. I can do this. So I have my 3. I could subtract my 5 to the other side, I suppose, to combine some like terms. I get -2 is equal to, I can distribute my negative. Oh, it failed. Well, hold on. Aren't we going to go find one more equation? Our equation has 2 unknowns. Then I'll have a little baby system to solve instead of an ABC system, just a system. Maybe it won't be that bad. It's like an XY instead of an XYZ. Hang in there. Have a little bit of faith. We're going to come back to this. Plugging in 1, we get 3 plus 4 plus 4. We can still use A as 1. 1 plus 4 is 5. So we still have 1 times 5 plus. Now plugging in a positive 1. B times 1 is B. B plus C times 1 is, oh, just B plus C. So I'll end up with 4 and 8 and 11 on that side. I can subtract my 5 again. 11 minus 5 is going to be 6. Okay, so maybe it wasn't as nice as the whole, here's A, here's B, here's C, but I think we can take this off to the side and be like, okay, well, that's not a big deal, though, because if I have B minus C is equal to -2 and B plus C is equal to 6, guys, isn't that a really fast elimination if we wanted it to be? I could just add down, so I have 2B equals 4. And Joe's already thinking like, oh, we can back substitute, right? So if 6 equals 2 plus C, pretty quickly. Yeah. Well, almost it. Remember, A, B, and C are the pieces that we're missing. And so how do we finish writing the partial fraction decomposition? Come back up, make sure there was no division where we had to collect anybody else. Then just say, oh, sweet. My partial fraction decomposition says, who's A? 1. 1 goes over x plus, okay, this guy's going over x squared plus 4. I need B to be with the x, so 2 goes with the x, and then C. Dun, 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 dun. That is the most that you can break down that original fraction. Could we have done a color coding thing where we multiplied everybody out and got all our x squareds and all our x's and all our constants? Yeah. But we would have had an ABC system, so 3 equations, 3 unknowns. Ugh. Would have been all right. But I think plugging in the zeros still makes it easier, even though we still have to do a little baby system at the end. So I'm just trying to give you tricks. I'm just trying to give you ideas. There are a few for you guys to ponder. We might not solve this guy all the way out. I don't think you necessarily need me to solve him all the way out. I just want to see if you guys would know how to form his partials. How would you form this guy's partials? Top is greater than bottom? No, it's a cubed over a squared. I just convinced Joe that he was wrong when he was right. Why was he right? Why is it proper and not improper? What if you foiled? It'd be a 4th degree. So isn't that, even though it looks improper, it's still proper because that would be a 4th degree. He is less than. Yeah. Poor Joe. I confused him. But what would the partials look like? Because some of you, hopefully, just a few of you are like, wait, aren't those imaginary like the other one? Because if you tried to factor this guy more, he doesn't go. It's going to be a square root of a -2. 8. I mean, yeah, we could write this side. You're right. We could write this side. But I'm curious what the partials would be. What would be over here? No, not x plus 2. We can't factor him. Okay. It's like linear where we're going to count up. We're going to do 1, and then we're going to do 2. Or I should say to the first power, then to the second power. But when they're saying A and B, I actually have to say they're wrong. What would go above this, guys? I wouldn't do ax plus c, but I would do ax plus b. And then cx plus d. Ooh. Is that going to get a little bit messy? Because now we have 4 unknowns. But what do you think our procedure still is to do next? Multiply to get rid of the denominator. Yeah. When you multiply to get rid of the denominator, you have 2 options, and I don't know which one's easier for you. Because do you guys see how many x's we'd have to plug in? No. How many unknowns do we have? We'd have to plug in 4 x's, and the problem is, do we have any zeros? Definitely not, because those are imaginary. Square root of a negative number. Now, if you like numbers, go for it. Plug in 4 different ones. You'll be able to solve eventually. But maybe it might be easier in this one just to do the color coding. I'm going to actually kind of start playing with it as I answer. I've seen a few hands as I try to answer some questions. Tyler, what's up? Because whenever we have one of these factors raised to a power, we have to count up. So we have to start with it to the first and then the second. Because long story short, the fraction could have looked like this and combined to become that, or it could have just had one of them, needed another one, and then combined. So we have to account for all the different possible, like counting up to the highest power. Yeah, whether it's linear or quadratic. I'm not showing all the work of multiplying both sides by this guy. I'm just going to do a dot, dot, dot. When you multiply both sides by this guy, you would get here. You could do x equals 0, x equals 1, x equals negative 1, x equals 2. And if you like numbers, that might be the best way to go, because you're like, I'm going to get all my numbers all plugged in, and I can go. I think, though, because you would get an A and a B and a C and a D and have no zeros to get you to any letters right away, you'd have a really nasty system if you went for 4 different non-zero x's. But look what happens if we just distribute. If we just distribute, I get 8x cubed. Maybe you'll see why I'm putting a 0x squared in just a second. There are technically 4 different types of terms that could have been there. Over here, when I FOIL, what we get is an ax cubed plus bx squared. I'm putting it in nice descending order. Plus 2 plus d. And when I go color coding, I can say, okay, I have an x squared term and an x cubed term and an x cubed. I have 0x squared with, oh hey, look, a equals 8, b equals 0. I'm solving for stuff just by doing a quick multiplication and comparing. So it's not always slower to go the multiplying out and comparing route. Now wait, we have a few more. We do have a couple x terms to get 13x. And we have a couple constants. But what you hear Joe doing is starting to compare and say, okay, well, 8 had to come from A. They're both x cubes. So I could just say 8 is equal to A using the red comparison. I can say 0, yeah, is equal to B using, there's only one term. It had to be 0. And then when I go over here to green and I say, stink, 13 had to come from 2A plus C. Wait, what do I know about A? I can plug in. (13 minus 16), C equals -3. Yeah, we can circle the B as 0. And then D, well, we do have to do that last comparison technically. 0 comes from 2b plus d, but didn't we just say b is 0? Well, 0 equals, sorry, that's a d. 0 plus d, well, d had to equal 0. It was actually one quick little playing, and then we're like, sweet. And we can end up with our final answer of 8x plus 0 all over x squared plus 2 plus negative 3x plus 0 all over x squared plus 2. What am I trying to show you? I love the plugging in zeros way because I like numbers, and I'm like, hey, this is fast. But depending on how many unknowns you have and how complicated the problem is, and how many zeros you do or don't have, it's not always the fastest way. Does that make sense? So how many ways do you have? Well, 2 main ones, right? 2 main ones. But don't they both start in the exact same place of having to factor the denominator, having to form your partials, having to multiply out the denominator, and then playing with what's left? One says, let's go start plugging in. The other says, hey, let's go start comparing and grouping the different types of terms. Now, guys, all that to say, there was one really, really, really cool trick that we skipped over a long time ago, aka yesterday at the beginning of class. But can you, just real quick, can you look at this example I gave you for this trick and compare him to what we just did? Is he easier or is he harder? No, look at him. Yeah, because look at his denominator. I mean, he's not bad, right? I could do x minus 2, and that's going to be an x plus 3 and an x plus 1. Are we good? I'm going to have 2 zeros. How many unknowns am I going to have? Oh, 2 zeros, 2 unknowns. It's going to be like boom, boom, and I'm done. So here's the sad thing. This trick only works for the easiest ones. So it makes the easiest ones even easier, but is it something you have to memorize and totally understand and use all the time? No, sadly. But it is something I wanted to show you because it is a trick. It's actually named after this mathematician, Oliver Heaviside. He was actually quite slender. I have a picture in my head, and he wasn't heavy. But anyway, Oliver Heaviside. It's called the cover-up method, or the Heaviside cover-up method, also known as the thumb trick. It's kind of snazzy, though, because it uses zeros, but it uses zeros in a really snazzy way. And so it only works with the ones with nice, distinct, no squareds, no cubes, no quadratics. The ones with nice zeros, like this one. What the cover-up method says is, if you are trying to solve for instance, the x plus 3, and who's supposed to be x plus 3, you can actually get there to who a is by covering up the factor you're trying to get to, writing down what's left, but instead of writing an x, you write the 0. You cover up the factor of who you're trying to solve. You plug in the 0, which is negative 3, to the both of the x's spots of whatever's left. Then you simplify. Negative 3 minus 2 is negative 5. Negative 3 plus 2 is negative 2. Oh, wait, a negative over a negative is a positive. A equals 5/2. Without doing any multiplying or grouping or zeros. It's kind of nice. So let's see if we can mimic the shortcut to get B. So with B, guys, who am I looking for? X plus 1. So who am I covering up? And I'm taking what's left, and I'm plugging in, negative 1. So I'm going to plug in negative 1 minus 2 over negative 1 plus 3. Whoever I cover up, his 0, negative 1. Negative 1 minus 2, negative 1 plus 3. I end up with negative 3 over 2. That's B, which might not have been very nice to solve for any other way. Now, I did want to show you one other thing. Even though this is a nice shortcut, which you may or may not need, you guys will get some fractions in homework for A and B, and they're not going to leave them like this because this is a nasty complex fraction. So I wanted to show you really quickly what they could do. There's a couple things they could do. One way when they're writing the answer, and trying to simplify it, they could just actually bring this down, the 1/2. They could make this like, instead of up there, they could do times 5/2 like that, instead of in the numerator. And so you could go ahead and have the 2 down be down in the denominator. You could do the exact same thing with maybe a minus instead of a plus and negative, 3/2. That is one way, which isn't totally bad. But technically there's another way that's a little bit easier, even though it looks worse. You can look at both of these and say, he has a 1/2 in him and he has a 1/2 in him. I can pull the 1/2 out and I can write what's left, which is just 5/x plus 3 minus 3/x plus 1. I think this is the preferred way that the book's going to be writing its weird fraction answers, just for you guys to know. If it's a weird fraction, if you can get it to be like a common denominator or have a common denominator, you can just pull out that fraction and leave the whole pieces behind. Is that cool? Okay. With that, guys, whew, took us a while. And it looks way worse than I think it really is, but partial fractions are done. Now, I did say we wanted to just barely start 7/5, but the nice thing is 7/5 is actually, yeah. It's an easier section than even 7/4 was, and definitely than 7/3 was. It's kind of nice to have a little bit of a breather here near the end. 7/6 gets a little bit nasty again, which is why today, even though we're starting 7/5, to be honest, I could almost do all of 7/5 right now in the 5 minutes left that we have. That's how quick it is. But we'll still talk about it a little bit more tomorrow. I'm not going to make 7/4 and 7/5 due on the same day. But 7/5 and 7/6 really go together, which is why I might have like a blended homework. Just getting you a peek into 7/6. And what's different? 7/1, solving systems of equations with substitution. 7/2, solving systems of equations with elimination. 7/3, solving multivariable systems of equations. 7/4, partial fractions, which had systems of equations. What 7/5 say? Not equations. Instead, inequalities. Wait a minute, inequalities. Greater than, less than, greater than or equal to, less than or equal to. Graph? Is anybody's brain going to shading? Tomorrow, you might want multiple colors in class, whether colored pencils. Highlighters get a little messy. One color isn't ideal. Because if we have a system of inequalities, there's going to be more than one. Eventually, maybe not right away. This first one only has one. But eventually, there's going to be more than one. And they're each going to have their individual shading. And we're going to be looking for the overlap. But just in general, just a quick review. Before we get to systems, we better make sure we can do just one, yeah? Isn't this a quadratic that's been shifted down one? Yes. So can't I just, in general, do a little whoosh, whoosh? Ooh, do you guys remember that with inequalities, sometimes they're solid and sometimes they're dotted? Since it's the or equal to, it's going to be a solid line, a solid boundary. If it was just greater than, it would be dotted instead. Solid indicates you're allowed to be on the boundary line. You're fine. Very unlike dodgeball. If you're touching that middle line, you can be pegged. Well, I guess it doesn't really matter. You can be pegged anywhere. What's another better one? Ooh, capture the flag. There you go. If you're touching the line, it basically counts as being over. There you go. You can be tagged. You can be on the boundary if it's or equal to. If it's not or equal to, you're not allowed to be on the boundary. But wait. The or equal to says solid. Graph is the greater than. Shading. One way of thinking greater is above. But be careful. As soon as we get beyond lines, the above and the below is not always so easy. Yes, it is greater. Yes, it is above. Sometimes not as straightforward as you would think. So there is a quick way to test and make sure you're shading the right apart, get nastier or weirder and you're not sure where the above is, like maybe a vertical line, where's the above? You can test any point, and I love testing 0, 0, which is the best point to test if it's not on the boundary. If it's on the boundary, I'm in trouble. Can't be on the boundary. But if I test the point 0, 0, all I have to do is plug it in. When y is 0, plugging into the equation, my question is true or false? Is 0 greater than negative 1? Greater than, I should say. If true, guess where I'm shading? Everywhere he is, the side of the boundary where he is. If it was false, guess where I would shade? The other side. So that's a quick little algebraic way to know whether or not you're shading the right side. But the greater above, the less below is usually a really quick shortcut. So some of you are like, okay, this literally is what, algebra 1? Well, okay, we could have harder things than lines and quadratics. But what's going to get weirder? What if you have multiple conditions, multiple inequalities? Now you have a system. Then we're going to try to find what's in common, and I call it the overlap. Which is why I'm saying bring different colors tomorrow. And it can be helpful, new vocab term, define the vertices of the solution, aka the corner points. Well, let me give you an example, as you guys are just writing. If, for instance, I had a line whose shading was below, and I had a parabola, let's do like a weird exponential function, whose shading is above, and I had another line whose shading is below. Do you guys see my overlap? Right here, right? Where all the shadings are intersecting. What would the vertices be? What's that intersection between green and red? What's that intersection between green and, green and black? And what's that intersection? Ooh, vertices or corner points occur at intersections. And if you guys have your calculators, is there a way to find an intersection on your calculator? Yeah, second trace. If it's by hand, aren't intersections the solutions to the system? Ooh. But maybe we're not looking for the intersection of all the different ones, but maybe just 2 at a time. Maybe just 2 at a time. Guys, this thing I showed you, don't worry, I didn't give equations. I just gave you a general idea. It was just a general example. But to be honest, you just got the main idea of all of section 7.5. So if you have time and your Wednesdays are busy, try to bust out 7.4 and 7.5. But only 7.4 due tomorrow. Sound good? Yes. All right, get out of here. Bye, guys. Nice. Excellent job. What, Matthew? Friday.